Good morning, everyone, and welcome back. I would like to continue with chapter 6, which is basically application of Newton's laws to one-dimensional motion. And so we're talking, it's called Dynamics 1, motion in one dimension. I'd like to continue with the concept of the normal force. I would like to explore it further, and the concept of weight and then weightlessness. And so we're going to consider what's called the elevator problems. And we're going to start with several cases. Maybe 4 or 5, I forget. So let's explore them. So elevator problems. So let's do case 1. Case 1. The elevator is at rest. At rest. So here is the elevator and it's at rest. So here is an elevator. So imagine you have an elevator here. There is a scale, meaning it's like a spring scale where if you stand on it, the springs get compressed and it will give you a reading. And so you're standing here, right? You're standing here. And let's say you're of a mass m, right? Your mass is mass m. And so the elevator is at rest. Let me do the case, actually the elevator could also be moving upward or moving downward at constant speed. At rest or moving, let's do all of them, all of these cases in one case because it's really zero acceleration, or at constant velocity. So the elevator will move at constant speed in a, obviously, straight line, either up or down. So that means the acceleration is 0. Your acceleration, the elevator's acceleration, everybody's acceleration is equal to 0 because it's either at rest or moving at constant velocity. So let's look at you, at yourself here, for somebody who is looking at you from outside, and they think, well, you're at rest, or your acceleration is equal to 0, then by Newton's first law, the net force on you has to be 0. And then you ask this entity, you're here, what could possibly be the forces on you? Well, the forces on you are, of course, there's gravity because you're on Earth, so gravity will try to pull you down, and the force of gravity is mg. And by the way, we will take this to be the positive y direction. The x direction is left and right, but the motion is up and down. So if you only had gravity, you have to fall. But you're not. Your acceleration is equal to 0. The net force is 0. So there has to be another force, and that force is a contact force. It's due to your contact with this scale here. You're standing on top of the scale. And the contact force is the normal force here, and it's upward. Okay? And so we would say that the net force is equal to 0. The net force is 0 because the acceleration is 0. The net force is equal to 0. We have two forces. There is the normal force upward, and so that's n. And then mg, it's downward, so that's mg equal to 0. And therefore, the normal force will just equal to mg. Okay? So the scale, we will call your weight will be the reading of the scale. Your weight or your apparent weight, we'll just call it the reading of the scale. So if you're standing on a scale, it will be calibrated to read mg. In your home scale or the bathroom scale, it will calculate mg and then divide by g to just give you the mass, because it will give you your mass in kilograms. But it's really recording your weight. So for this first case, when the acceleration is equal to 0, the normal force is just your weight. So it's equal to your weight, your true weight. Okay. Let's do the second case. The second case, you might be able to guess it. The acceleration is 0, so we would like the acceleration to be not 0. So it's really, there are two cases, but this second case we will break it into we'll break it into 3 cases. So we'll call it case 2. Case 2. Elevator accelerates upward with an acceleration a. The elevator accelerates upward with an acceleration of magnitude A, right? Accelerates upward with an acceleration A. That means the elevator could be moving upward and speeding up. So the acceleration is in the upward direction because your velocity is this way and the acceleration is this way, so you would be speeding up. Or maybe the elevator is going down but slowing down. So if you're going down, your velocity is this way, but you're slowing down, it means the acceleration is in the opposite direction to the velocity, so it's this way. So in both of these cases, either you're going up and speeding up or going down and slowing down. Both of them have an acceleration that's upward. So let's look at you here, standing in the on top of the scale here. Here's the scale. Here you are. Okay, here you are, and your acceleration is in the upward direction. By the way, again, the y direction is always upward. Okay, and we ask, what are the forces on you? Okay, what are the forces on you? You might say, well, the elevator is connected by chains and belts, and so those belts are pulling. But what are the forces on you? Those belts are not in contact with you. So yes, they are in contact with the elevator and they cause the elevator to accelerate, but they're not directly on you. Newton's laws, to apply them, you have to consider only the forces on yourself. So what are the forces on yourself? So let's draw a circle around you. Just isolate this body that we're interested in, the person here standing on the elevator. And of course there is gravity downward, force of gravity. As long as you're on Earth, there is the force of gravity, and it's equal to mg. And then you're in contact with this scale, so there has to be a normal force. The normal force always pushes you away, right? The scale is applying a force on you, and it applies it perpendicular to the surface of the scale, so it's this way. That's the normal force. Okay? And so we would apply Newton's second law. It says the net force on an object is equal to the mass of that object times the acceleration of that object. All right. So the net force on this object, which is u, let's call it net force, is equal to the mass times acceleration. And here the net force is all in the y direction. So, all right. So the net force consists of a normal force in the positive y direction, and then an mg downward is equal to a mass times acceleration. The acceleration is positive, so I just put ma because it's in the upward direction. And therefore, the normal force from the scale will be equal to mg plus ma. So the normal force is just m times g plus a. So earlier, when the acceleration was 0, the normal force was just equal to mg. But when you're accelerating upward, the normal force will be slightly more, which makes sense, because if you remember, if you don't, try to observe it next time when you ride on an elevator. So when you stand on an elevator, you hit up button, let's say 20th floor. When it starts going, you feel heavier. You feel like you're pressing against the floor because the floor is pushing you harder. Because that's how you would accelerate. You're accelerating upward. You need a net force in the upward direction. Gravity is downward, so the normal force has to counter gravity and add some more. Because if it only counters gravity, the net force will still be 0. So we would like it to counter it and give you some more. So the normal force has to equal to mg plus some more in order to accelerate. That's why you feel heavier. The same thing when the elevator is going down and it's about to reach the floor you want, so it starts to slow, the acceleration is upward, you start to feel heavy again. Okay? So that's that. Let's go to the third case. You might be able to guess. Third case would be an elevator that is accelerating, but it's accelerating downward. Case 3. By the way, your apparent weight here, this is your apparent weight, we call it the normal force, is the mass g plus a. So it's slightly more. When you're accelerating downward, there will be a minus sign here. We'll see it in a moment. So the elevator accelerates downward with an acceleration A of A. It's downward. So, all right, so here's my positive y direction again. Here is the elevator. Here is the scale on which we're standing. Okay? And the acceleration is downward. So it's really, it's equal to a negative number, some negative number. So this is the magnitude of acceleration. The acceleration itself, if you want to write it as a vector, it's equal to minus a j hat, because j hat is the y direction. So if you like to write, in this case, it's a is equal to a j hat, positive, if you like, positive a j hat. And the normal force is n j hat, and the force of gravity is mg, negative mg j hat, if you like. Anyways, so what are the forces? Well, let's isolate the person or the entity we want to study. And we say, all right, there is still gravity, you're on Earth. Earth will pull you down. That's the force of gravity. It's equal to mg. Again, if you like to write the force of gravity as a vector, it's the force of gravity is minus mg j hat. If you want to write it that way. In fact, let me do it this time this way, just to emphasize something, the vector nature. Okay. And then the normal force is upward, as usual. That's the normal force. And if you want, you can write the normal force as a vector. That's the normal force. And so we can write the normal force as a vector that's equal to just n j hat, so because it's positive. Okay. And so we will say the net force, F net, I'll write it with a vector sign, is equal to the mass times the acceleration with a vector sign. Right? I'll just show you what we did kind of, and what you're doing really when you write those minus signs. The net force is equal to the normal force, j hat, and then plus the force of gravity, which is minus mg j hat, minus mg j hat, equals to the mass times the acceleration, which is negative a j hat. So you see, everything contains a j hat, so I would just drop the j hat. So normally we just write this, the normal force minus mg equals to minus, oh, I forgot the minus the mass times the acceleration. The acceleration is a j hat with a minus sign, so minus ma. So this is what you're doing. So you move this to the other side, then you get the normal force is equal to mg minus ma. Minus ma. So the normal force will equal to the weight, but instead of being plus a, it's minus. Instead of being plus ma, it's minus ma. So the normal force will equal to m times g minus a. Okay. So that's your weight. Your apparent weight will feel lighter. And that's what happens when either you're going upward and then you're about to reach your destination, the elevator starts to slow down, that means the acceleration is downward, then you feel light. When the elevator stops suddenly upstairs, you feel light. Or when you hit the down button, and then the elevator starts to accelerate down, in the first moment, you feel light. That's what's happening here. And then finally, the fourth case, case 4, the elevator is in a free fall. So let's say the chains that are connecting the elevator, they just snap, and the elevator just falls, and you fall with the elevator. So you're in the elevator is in a free fall, and you're in a free fall, meaning everything is accelerating downward with an acceleration equal to g. It means the acceleration here is really negative, is equal to g in magnitude, and so it's negative g j hat. So here is the case. So again, the y direction, positive y direction is this way, and here is the elevator, and here you are standing here. So let's isolate, and we say, all right, Again, I will not do this one with the vectors because we already did it. In fact, it's going to be exactly this with an acceleration equal to g, so you get g minus g equal to 0. And I will explain in a moment why that makes perfect sense. Your weight will appear to be 0. You'll be weightless. So again, you will have an mg downward. That's the force of gravity on you. And then there could be a normal force, and we want to find it. And then the acceleration here, the acceleration is equal to g, but it's downward. So we say the net force equal to ma. The net force will equal to the mass times the acceleration. And the acceleration is, since the acceleration is negative, we will put a minus sign here because it's downward. So you have minus minus mg. The acceleration is equal to g. So minus mg because it's downward. And the net force consists of the normal force upward and then mg downward minus mg. And so the normal force will equal to mg minus mg, and that's equal to 0. So the scale reading, the normal force from the scale on you will be 0, which makes perfect sense, and it will appear to be weightless. Because, so for example, if you have a pen like this, and you're in a free fall, and you let the pen out of your hand, the pen will, relative to you, it will stay at the same height. Because you're falling, the pen is falling, and so it will appear to be weightless. It will just appear to levitate on top of the ground. But the reason for that is because the pen is falling, and the elevator itself is falling, and everything is falling, so it appears to be weightless. It appears to be weightless. And it makes sense. So imagine you take a scale, tie it to your shoes, tape it to your shoes. Don't do that, but if you were to do that. So you tape the scale to your shoes, and standing on a table, let's say, and the scale is taped to your shoes, the scale will read your mass. It will give you your weight. It will give you your weight. Now, if you jump, let's say you're jumping, and the scale is tied to your feet, how much will the scale read? Well, you're falling, the scale is also falling, so you didn't give it a chance to press against it. It doesn't get a chance to press against you, so it will read 0. That's all this is saying. It will appear to be weightless. Okay. So that's that. And now so I'm done with this normal force. I would like to talk about the frictional force in the next board here. Okay, so I would like to talk about static friction now, and kinetic friction. And so static, kinetic, and rolling friction, basically 3 types. So I will start with the static friction here. I have a block here that is, it's 5 kilograms. It's pretty hefty. Yes, 5 kilograms, about 11 pounds. So here it is. I'm going to push the block. I'm applying a force to the block. So first of all, when I don't apply a force to the block, the net force on the block there is 0 because the block, first of all, is not moving. Yes, there is a normal force because it's resting on a table, and there is an mg downward because it's on Earth, but those add up to 0. But let's consider the force of friction. Let's consider the force of friction. What would the force of friction be? Well, right now the force of friction is equal to 0. Is equal to 0 because I know that there is the normal and there is the mg. That's it. Otherwise, if we have a net force, then things will start to move. Now I'm going to apply a force this way. Newton's second law says if the net force is not 0, then the object starts to move. But I'm applying a force, and this mass has not moved. It means, since my force is this way, there has to be a different force that's the opposite way, and it's exactly equal to my force because it cancels it, and the net force is 0. I increase my force. I'm going to increase my force. So the object still hasn't moved. And then up to a certain force, so let's say I take my force, let's say it's 0.1 newtons, it hasn't moved. 0.2 newtons, 0.3, 0.5, maybe 1 newton, 2 newtons, 3 newtons, 4 newtons, 5. At 5 newtons, let's say, it started to move. So that means that force, every time I increased my force, there was this force that's opposite to it has increased, in order to cancel it. How do I know that that force exists? Well, simple. If this were the only force in this direction, Newton's second law says you have to accelerate that way. It hasn't accelerated, it means somebody has to cancel it, and that's the force of friction. It's due to imperfections. I might give you a deep dive into it, but for now, let's just say you got the force of this called static friction because the object there is no relative motion between the two surfaces. The object hasn't started even moving, and it's opposite to the direction of the force I apply. Before I started applying the force, that friction was equal to 0, so I would give it the force of static friction, I would call it Fs, the force of static friction. It starts at 0, and then I increase my force, and I increase it, and I increase it, until it reaches some maximum force, and then it breaks loose and starts moving. So it has the ability to take values between 0 all the way to some maximum value called Fs maximum, some maximum value, and then it starts to move. If you go beyond this, it will start to move. Now, how much is this maximum value? That maximum value is proportional to the normal force. For example, if I do this, the object will start to move, let's say, I said 5 newtons. But if I put more mass on it, and I push, it will take maybe 20, 30 newtons. So it's proportional to the normal force, because when let's say you have these two surfaces and there are imperfections. Here's the first surface, here's the second surface, and they look like this. When you increase the normal force, you lock them together more. And then, so it's hard. These teeth, you have to break loose like that, and then you start to move. I always think of it as, let's say you have a friend and you're trying to save them, they're about to fall off of a cliff. So you're giving them your hand and they clasp to it like this. That's static friction. And you can pull and pull and pull, but if they are beyond, if the frictional force, if these two forces they have certain maximum, right? Everybody has a certain strength that you can, like if you do deadlifts, there is a certain amount of strength that you have. Beyond that, you can't. So if you make the person heavier and heavier, then you break loose and the person falls. Then, when it starts to move, it comes into the kinetic friction. So, this maximum value is actually proportional to the normal force, and the proportionality constant is called the coefficient of static friction. That's the coefficient of static friction. And this coefficient of static friction here, I have them summarized in the table, depends on what's on what. And it's actually not really exact. And there are tables that are more, that are longer. So for example, it says rubber on concrete, tires on dry concrete. The coefficient of static friction is about 1. In fact, if you heat the tires and so on, you can make it like maybe 4. You can make it even larger than that. Rubber on concrete, if the concrete is wet, well, the friction reduces, it's slightly less, 0.3, the coefficient. Steel on steel, 0.8. Wood on wood, 0.5. Ice on ice, 0.1. And as you know, this is static. As you know, once you start the object moving, it's easier to move it. Because, I don't know if you ever tried to clean behind your fridge or move your fridge. It's harder to start it moving, but once you start it moving, and it's moving, it will be kinetic friction, and the coefficient is typically less. So look here. The coefficient of static friction, coefficient of kinetic friction, it's less, 0.8 and 1, 0.25 and 0.3, 0.6, 0.8, 0.2, 0.5, 0.03 and 0.1. So typically less than it. So that's the static friction. We will do problems on it in a moment. So static friction takes a range of values. Kinetic friction, on the other hand, is the force of kinetic friction. It simply takes one value. Once you start it moving, it's moving. It's equal to the coefficient of kinetic friction times also the normal force. But notice it doesn't go from 0 to some maximum value. It's always one set value. Before there is relative motion between the two surfaces when they are rubbing, if they are rubbing like this, then it is kinetic. Before they started rubbing, then it is static friction. Okay? All right, so that's the kinetic friction. How about rolling friction? Rolling friction is called the FR, and it's the coefficient of rolling friction times the normal force. So here is something that can roll. Here is a hoop, like a tire, and I started to roll. Hopefully it stops eventually. Okay. It doesn't want to stop. All right, so as it rolls, typically, or here's a piece of chalk, as it rolls, eventually it comes to a stop because the rolling friction is opposite to the motion, and it will cause it to slow down. Now, what are the properties of friction, or what are some of the properties of friction? Some of the simple properties of friction, topic of friction is, if you want to be exact about it, it doesn't just take one value, right? It depends on many things. So typically, the friction will depend only on the material, on the two materials, and it doesn't depend on the surface area. For example, if I take this block and I make it smaller surface area, it will still be the same friction as long as the normal force is the same. As long as it's the same materials, the same normal force, the friction will be the same. So it doesn't depend on the surface area. So whether, for example, my hand, if I take my hand and rub it this way, there is friction, and if I take it on the smaller, on the narrower end, it will still be the same amount of friction as long as the normal force is the same and the material is the same. And it also, the coefficient of kinetic friction does not depend on the speed. Once it starts moving, it is what it is. It will take just one value. The same thing for rolling friction. Okay, and the force of static friction takes a range of values here. So static usually has the larger value, kinetic smaller, and then rolling is even smaller. Because again, something rolling, it's typically much less. It will roll much longer than if I just do this. Let me do it this way, then it stops quickly. This is kinetic friction, but this is rolling. Rolling is way less, is much less. This is kinetic. Eventually it stops, okay? So here is an example I would like to do. I just want to show you the demonstration. So it says here, Carol pushes a 25 kilogram wood box across a wood floor. So it's wood on wood. Wood on wood, if it's static friction, it's 0.5, but if it's kinetic friction, it's 0.2. In this case, it's kinetic because Carol is pushing the box at a steady speed. So here's the box, let's say. Imagine this is steel, but imagine it's wood, and imagine this is wood also. So she's pushing it at constant speed. And the speed is 2 meters per second. So if the speed is constant along a straight line, it means the velocity is constant. If the velocity is constant, then the net force has to be 0 by Newton's first law. So how much force is she pushing with? And then, let's say she's pushing it 2 meters per second, and then she lets go. It will stop. After she lets go, how far will the box go before it stops? All right, so let's do that. In fact, let's do this problem in the next video. I'm running out of time on this one.